Okay, so as indicated in a previous video, now we discuss how you can use molecular dynamics to simulate damage, first at low energies and then at higher energies. And actually one of the key points of this is that from these molecular dynamic simulations one can get a lot of insights into how collision cascades actually behaves and how the damage is produced physically. So first, the case of low energies. If one has a bare low energy just above the damage production threshold, then it's pretty easy to understand what can happen here. And in this case, we will have one of these atoms in this very small simulation cell simulated with density functional theory molecular dynamics will be given a recoil, and you will see when I start this what happens in this simulation. Sorry. So you see that the atom received a recoil energy of 16 eV. It moved to towards the right, and as you probably are not surprised, because it was above the threshold, it stuck into an interstitial position and left a vacant position behind it. So this is in principle pretty simple, and one gets a simple Frenkel pair from this kind of process. Well, now we start also going into the physics of it all. So what this animation and all the MD simulations which will be shown in this chapter show is the production of primary damage. And this means the damage produced initially on the sub-nanosecond timescale and does not include damage recombination by thermally activated processes. And this is in a way not always realistic for the macroscopic damage production processes, because in many cases there are lots of thermally activated processes going on after and in between the primary damage events, and these can actually dominate completely the outcome of the radiation on the macroscopic scale. But anyway, it all starts with the primary damage, so it's important to understand the primary damage, and sometimes the primary damage is actually also the total damage. Typically, this is at low temperature, below the defect migration temperatures, or if the solid is very hard bound, for instance, hard bound covalent solids, there often is actually not so much migration even at room temperature. So now we will use these molecular dynamic simulations to illustrate and understand the primary damage. So here is now another low energy event. This time in graphene, where a single atom in the graphene was shot upwards, and as you see, there is a complex regeneration process, and at first it seems like everything is perfect, but if you look carefully you see that perfect graphene has only 6-membered rings like here and here, but in this process you actually got a 5-member ring, a 5-member ring, and a 7-member ring and a 7-member ring, and this is known as a stone Wales defect and has also been directly experimentally seen in graphene. These simulations are run by Jani Kotakoski, who is an associate professor at the University of Vienna when I'm doing these video lectures. But then if you increase the energy, these processes become more complicated. So this is now a case from the molecular dynamics at about 10 times the threshold energy, and now you see that single ion can already put lots of atoms into motion. You have sputtering atoms flying out. It's a fairly complicated process already. Well, actually this particular animation has a cheating feature in it. It was done for school animations, and if you look closely, you can figure out that there is something which is not correct or is a bit misleading in this animation. I'll be silent for a moment so you can think about what it would be. Well, if I'm not sure you managed to figure it out, but the point is that this was supposed to be a cross-section However, in this case, there were atoms, actually, if you look closely, there are atoms on top of each other. So in this case, when making the animation, when you do a cross-sections, atoms jump in and out of the plane. But for these school visits, I made a version where actually every atom in the initial lattice is shown no matter how long, where it goes. And this is, of course, misleading. In reality, this area was actually filled by atoms, so this is indeed a misleading animation. Now, in the rest of the animations, I won't do this misleading trick, so these are as realistic from a plotting point of view as they can be. So now if you go higher in energy, in the previous case you could see that the atoms collision still, you could sort of count the collisions and it was almost like a binary collision process. But now if you go to even higher energies, take 10 kV recoil in gold, things will once again look different. So now you have this gold self-recoil, the colors are now the kinetic energy scale like in the previous case, and now you see that there is actually a huge set of collisions here, and it's not really even collisions. Now you see that atoms are moving pretty much like in a liquid. And this is indeed the case. This is liquid-like behavior, and this has been shown by analysis of this, and I'll show you some key results which show that this is really like a liquid. So now we cannot talk anymore about ballistic collisions, but really about a very high temperature, high pressure thermodynamic process. Now you see here that the lattice does regenerate almost perfectly also after these collisional processes. And here you also see this time scale I mentioned. So in this case, we are now approaching 30 picoseconds, and now the lattice has cooled down. You can say that in this case, the time scale of this heat spike was about 20 picoseconds, and after 30 picoseconds, everything has cooled down and frozen in. And by analyzing this kind of simulations, one can really get good insight into the physics. And this plot is the first one, which has actually several interesting features. This animation and analysis was done for a system where the ambient temperature deliberately 0 Kelvin to be able to see sort of the pure heat spike effect, guaranteed to not have any equilibrium thermodynamic effects in it. So what if you first look at the black curve here, this is the temperature in the whole system, and you see that the overall trend here is decreasing, and after eventually it cools down back towards 0 Kelvin. You note that this is a logarithmic time scale. So initially this about here, this region here is the ballistic phase, and then after that you get into this heat spike-like phase. Now you are probably wondering about these strong dips in the temperature. And that can be understood if you look at the blue curve. This is the maximum kinetic energy of any atom in the system. So initially this was of course the 10 kV of the recoil. And here you see that you start at 10 kV, it slows down a bit, but after already 2 femtoseconds there is a huge dip in the maximum kinetic energy. Then it's stable for a while, a small dip, a big dip, and several dips here. And this is perfectly realistic. There is a simple physical explanation to this. What happens is that if you have a strong collision between two atoms, then of course at that point they go up in potential energy and slow down, go down in kinetic energy, and this is visible here that the kinetic energy is decreasing in these strong collisions. And because the temperature is the sum of the kinetic energies, the temperature graph has a similar behavior. The temperature in the whole system has dips whenever there is a strong collision between atoms. And this is true in the ballistic phase. Then after the ballistic phase, you only have these many body collisions, and then these dips vanish because you have a large body of atoms, hot atoms moving collectively, and then there is there are no dips anymore. Finally, you may wonder here, after a long time, after 5 picoseconds, why is the top in the temperature in the system? And this was explained by Herbert Urbasek, professor in Germany at first time, about more than 20 years ago. This, sorry, not dip, but increase. Where is there an increase here after as long as 5 picoseconds? This is caused by the fact that after the heat spike, you have many defects left, But when the heat spike recrystallizes, some of the defects which are high in potential energy recombine, and then potential energy is freed up to become kinetic energy, and that then is visible as an increase in the temperature in the system. Finally, the final physically interesting feature in this plot is that you see that the maximum kinetic energy after about 200 femtoseconds is extremely small. It's around 10 electrovolts or so. This also shows that you really go into a thermodynamic behavior when there are no high kinetic energies left. So this illustrates the point of thermalization, which means that after the ballistic collision you become a thermodynamic system, and equilibrium thermodynamics comes into play. And this was first analyzed in detail by Wheelan Xu and others in 1995, published an analysis of the kinetic energy of the atoms in a heat spike, and showed that after about 1 picosecond the kinetic energy follows a Maxwell-Boltzmann distribution, corresponding of course to a high temperature. In that case it was about 2000 kelvins, but still this is at the thermal distribution of kinetic energy is the same as in a regular solid or in an ideal gas. So after this thermalization, the cascade is still very hot. You can analyze temperatures around 5 or 10,000 kelvins, depending on where you do the analysis. This is showing the temperature at 0.25 picoseconds. But it's important to understand that this is not an equilibrium temperature yet, because the system is not yet fully thermalized, and it cools down on sub-picosecond time scale, so this is not a similar equilibrium temperature as normally. If one is some people are nitpicking on saying that this is not temperature at all, but what you can do if somebody is nitpicking on this, that you can say that this is kinetic energy per atom in the heat spike region in units of Kelvin. But another proof that this really is like a liquid is that an analysis of the pair correlation function of the material, which shows that indeed the pair correlation function in one of these heat spikes is very similar to what was earlier calculated for liquid copper with the same interatomic potential. Now you saw that this heat spike was this hot collisional region was cooling down, and then the next logical question is, how does it cool down? Well, in this simulation, the main cooling down is lattice heat conductivity phonons. Also, there was cooling by electronic stopping power, but moreover, in reality, there can be also electronic heat conductivity, that is, hot atoms heat up the electronic system, and then the electrons in a metal are very good heat conductors, and they can cool down the system further. And this electronic heat conductivity was not included in these MD simulations I showed. Finally, if you have a cascade near a surface, sputtered atoms will of course also carry away kinetic energy, and this will also cool it. So the question is, which cooling down mechanism dominate? If you have a very good insulator, then there is lattice heat conductivity will dominate because there are no free electrons. I mean, the cascade can excite some electrons into the conduction band, but their contribution is very likely to be small. In metals, the electrons are of course free, and they can have a high heat conductivity, and it's possible that some of the cooling occurs via electron-phonon coupling, which is in general the methods by which the electronic temperature and atomic temperature are coupled. In this case, I emphasize that what happens due to the ballistic collisions, the atomic system heats up first, and then this transfers energy to the electrons. And because the electrons are much lighter, their heat conductivity is much better than that for the atoms. Well, how important the electron-phonon coupling actually is in cascade cooling is still not fully clear. But there are indications like analysis of ion beam mixing, that they can be very well reproduced with MD simulation without any electron phonon coupling, and this indicates it's not overly important. But there must be some electron phonon coupling, and there are recent works where it has been analyzed in some more detail, actually also more recent work than this, and it looks like it has an effect, but the dominant cooling is still the lattice heat conductivity. Well, and all this leads to the concept of a thermal spike or heat spike, and I mentioned this already several times. But now I'll explain still a little bit more what that heat spike means. So it means this hot region. The interesting thing is that it was first predicted in 1954, when of course molecular dynamics method was not even invented, but Brinkman back then had an idea that when you have a hot high energy ion, it will kick out atoms from it, and then put in interstitial atoms far, you will have an underdense region in the center and an overdense region around it, and this started the discussion of so-called Brinkman spikes or heat spikes. And later on, in the first MD simulations of cascades, when were done by Thomas Diaz de la Rubia by bulk cascades, 1987, they showed a similar behavior to this. They indeed showed this underdense region, which was also visible in these animations I showed earlier in this lecture. One note, these word thermal spike or heat spike, they are essentially used as synonyms, and both are widely used. So I don't think there is any difference. It's just a matter of convention whether you call it thermal spike or heat spike. I myself tend to talk about a heat spike because it associates with these really hot temperatures, whereas the thermal temperature may of course be much lower. But yeah, so this issue that the heat spike is underdense in the middle, it's visible in these animations. This is from the same animation as was shown earlier. But you can of course also analyze this, and there is analysis indeed that the density is highly underdense in the middle and overdense in the core around it. So that was molecular dynamics simulation evidence, but there is also experimental evidence that heat spikes exist, and I'll mention here a couple of maybe most convincing ones. First of all, there is experiments on irradiation. Certain dense ceramics show that after irradiation, there are new crystal phases which appear, which are otherwise known to form only at high temperatures. So it's very difficult to explain how these would occur under irradiation if not for heat spikes. And then there is a nuclear physics measurement technique in iron, which actually gave a lifetime measurement of about 6 picoseconds for a liquid phase in iron. Unfortunately, this nuclear technique only works for iron, so it hasn't been generalized to other metals. But anyway, this is very compelling evidence that the heat spike lifetime is indeed around 5 to 10 picoseconds. MD simulations in iron give very similar results, the values to these 6 picoseconds. But these thermal spikes or heat spikes, they are not always formed. In a very light material like lithium or carbon, there is never a thermal spike in the sense that you would have a pocket of metastable liquid material. The reason comes from the ballistic. Due to the ballistic collisions are just too underdense for this. And to illustrate this point, this is an image sequence of silicon, germanium, aluminum, and gold. And these are good comparisons in that silicon and germanium have the same crystal structure, not so different lattice constant, but germanium is of course heavier. Similarly, aluminum and gold actually are very similar lattice constants, but aluminum is much lighter than gold. And these are same energy cascades, 10 kV, so you clearly see that silicon and aluminum, the damage is quite widespread, where germanium and gold is quite dense. And here is animations of these same things. So this is comparing silicon and gold, 10 kV cascades, red atoms being hot. This is now a 3D plot. And you can see that indeed in silicon one has small, more or less isolated damage pockets, whereas in gold you have a single, very dense, pocket. And then a similar comparison, germanium and copper. Here germanium and copper have almost identical masses but different crystal structures, so this illustrates that also the crystal structure, the germanium has a much more open crystal structure than copper. You see that the germanium cascade is less dense, it's denser than silicon but clearly less dense than copper, which had a pretty much exactly spherical spike. And looking at these animations, you really see that many of the liquid atoms regenerate into perfect crystals, so they don't produce damage at all in the metals, whereas in the silicon and germanium you are left with a lot of damage. So this damage recombination, that's an interesting also to compare different kinds of materials. First of all, you can analyze the number of Frenkel pairs produced with the Wigner-Seitz methods as a function of time. And these analyses in metals practically always give a curve like this. First you have a strong increase in the ballistic phase, then a maximum, but then there is a huge recombination, which was visually visible as these liquids region recombining, but if you analyze it, the number of atoms which are in the heat spike in incorrect positions, you get that you can actually have almost a factor of 100 recombination. And this is known as athermal defect recombination, where athermal means that the effect occurs without any thermal activation. So even if the ambient temperature is 0 kelvins, this happens. And as you can see, it's a very strong effect in metals. However, then in other materials, it's not nearly as strong. In silicon, the recrystallization is much less efficient, and this is actually known also from non-radiation studies of the recrystallization of materials. That if the recrystallization is very efficient, the damage has time to recombine. If it's not, that this liquid zone doesn't have time to recombine, and it freezes into a disordered or amorphous region. And this latter behavior is typical in semiconductors, and it's been seen in silicon and germanium and gallium arsenide, where you see that indeed you can see this is I think was germanium. You see that you can get quite large damage pockets from single irradiation events. Also, these MD simulations show similar behavior, small amorphous pockets formed directly in these cascades. Well, then the ionic materials, they can be more like metals or more like semiconductors. Usually there's somewhere in between. So for instance, in tungsten carbide, it looks like it's, you have a fairly large heat sky because it's a dense material, then damage does recombine, but not completely, and you have some actually ordered damage with this. And different ionic materials have big differences. And this is not fully understood, but it's clear it relates to at least the atomic packing fraction of the materials. And this references some detailed discussions of the reasons why different ionic materials are different. And just to illustrate this point, here is one more animation of a 5K cascade on the left side in tungsten, a metal, and on the right side in tungsten carbide, a ceramic material. You see that initially the heat spike looks quite similar, but in tungsten practically everything recombines, as you can see, given enough time. But whereas in tungsten carbide you are left with a fairly large damaged region. This damaged region then on macroscopic timescales at elevated temperatures still recrystallize, but the primary damage state is at least very different. Finally, for this nature of heat spike discussions, tell that this original historic picture of Brinkman is correct in the sense that yes, interstitials are pushed outwards, then they return almost fully, which Brinkman didn't quite realize. But if you look at a bilayer system, you can sort of prove this point that vacancies are pushed towards the center. In here you have vacancies everywhere, but then when it recrystallizes, it's not energetically favorable to leave behind a vacancy, so they are pressed towards the center of a cascade. And this can be proven by looking at a bilayer system with different melting points, because then the higher melting point material, in this case cobalt, of course recrystallizes faster, and then what happens is that the cobalt will press the vacancies onto the side of the lower point material. In this case it was copper, so you can see an asymmetry at the interface, which really proves this point that vacancies are pushed towards the center. And this also explains why vacancies tend to cluster, because they are pushed towards the center and then find each other there. But interstitials may also cluster, but the effect is not as clear. And now I'll show again an animation which was shown earlier on this course. So now after all these discussions, we can pretty much understand what's going on here. So here you have the heat spike, a little bit of an underdense region, recrystallization going on. And in the end, then, in this case, the vacancies are pushed towards the center, but actually are not left in this region, which was plotted here. But you do see complex crystal structures here. These are actually a direct production of dislocations from this collision cascade. This is either interstitials or vacancies which were pushed towards an ordered structure similar to a well-ordered dislocation loop. And this is something which these dislocations will also be discussed later on in the work, the course. But yes, so this now concluded this first video on molecular dynamics and the physical mechanism of damage production. And then in the next video we will look at how this can be used to understand total damage production as a function of damage energy.